Okay, let's do some applications of induced current. The three we're going to talk about are generators, transformers, and metal detectors. So let's kind of start off talking about those. Generators, if you want to see a classic form of a generator, this is kind of it. So you would spin something would somehow make the wires spin in this magnetic field created by this magnet. As it spins in the magnetic field created by this magnet, you would then get a voltage across here. That voltage induces a current, and you've got electricity. You can light up a light bulb. That's kind of traditional way it would look. Now, if you want to see it with some more coils, and actually the way they have to work, there's slip rings in these things and stuff. So remember, as it spins, one way you get electricity going one way you get it going the other. So generators actually produce alternating current. That's one of the reasons Tesla, beat basically Edison. Edison wanted direct current, Tesla wanted AC current for multiple reasons. One is it's easy to generate. But here, I'm going to basically be turning these coils of wire that you can see inside here. Here's a magnet to create a magnetic field. And on this plate here, it's got a little coating that will glow when there's electricity on it. So, as you can see, depending on the direction, as I'm turning these coils, and there's a little gearing here, of course, to make it rotate faster. And you can see current going one way, current going the other. On this side, it produces positive on the voltage, and on the other side, to get it, they don't light up at the same time. Of course, and the faster you go, the brighter. All right, you get it. You got the idea. That's a generator. What you have at your house, if you've got one, or what you see at a nuclear power plant or electric power plant, is basically a big, giant version at the power plants. And one of the reasons generators are so expensive, it's not just a motor that they have. Normally they just have like a Briggs & Stratton or a Honda motor. If you have a small Honda generator, those are nice for camping. But what happens is you got the motor there. That's part of the money for it. The rest of it is the coils of wire and the magnets to turn it. Those are expensive, and they're heavy as well. A good generator is, produces a whole lot of current, like the one I have for the house. It's heavy. It takes two people to lift it up and everything. So you don't take, that big generator for your whole house on a camping trip. Use little small Honda generators. All right. So let's look at generators a little bit more in detail here. Generators are formed by moving that coil of wire, and it goes through, 0, 90, 180. So that's, it's a coast. It's positive here, negative over there. So, and it's the rate of change of that magnetic field. It's the rate of change of it. So, actuality, what you get here is, and let me get the red sheet of paper. This induced EMF in the coil, which is, just your delta V, your voltage. This is going to be equal to, and they show how they get it in the book, that's the rate at which you're turning it, the angular rate, omega, the area of the coil, how big the coils are, strength of your B field, your number of coils, N is the number of coils. This is the area of the coil of wire. Of course, it's rotating in there, what area we've talked about. That's how fast you're rotating it. And sine omega t. And omega t is just the argument of the sine function. That's how fast it's, omega is how fast it's angular frequency, and times time. And that will basically give you that oscillation. So it goes from -1 to 1. This function goes from -1 to 1. So it doesn't add amplitude to it, but it will just show the oscillation from it. That creates that AC voltage. Of course, the faster you spin it, more potential. That's why you need that big honking motor. Of course, the area of the wire, of course, the bigger area, more of that. Another reason to have a big, for a big generator, you need a big area of that coil. Of course, strength of the B field, that's going to be constant. Better magnets, stronger magnets, greater induced voltage, and number of coils. And that's just adding more turns of wire. And that, of course, turns of wire equals money. Okay. They have a little example problem in here you can do. It's basically they just stick it in there. Voltage you want, of course, this voltage becomes a current, and when it runs through a wire of a certain resistance, most generators are rated on how much, they're rated on power, but really it's based on current they put out at 120 volts, and based on that current, then they can handle lots of different things. If you want one just for small, some small little camping one, it can run, your TV and a few small appliances around. But if you want one to control your AC and your refrigerators, things that pull a lot of current, then you need to get a good $500, $600, $700 one at least, a really nice one. All right, that's a generator. Now a transformer. And no, Cameron, I'm not going to switch this around and make it be something else. Alright, Jerry, yes. There is difficult and it is more than meets the eye. But you old school guys, you know that. I mean, you might get that joke. Angel, you might get that. Torres. Dayton, you get that? Wake up, Dayton. Thank you. Alright. Now, transformers. Now, a transformer, the type we use in physics anyway. There is no Optimus Prime in what we do. What we're going to do, a lot of times you'll see kind of a squarish or rectangular-ish piece of iron for that. And what you'll do is, you'll have some coils of wire on one side, coils of wire on the other side. And then you'll put this to an oscillating source. So I have basically, it's like a light bulb, but I've got a sine wave in it, and that means it's something, a source of a AC voltage. It could be a generator. It could be your, what's coming out of your wall or something. But with an AC source, what you got over is on one side. And on the other side here, we're going to put a voltmeter. You're going to put a voltmeter there. And this side is known as the primary. Those would then be the primary coils. These would be the secondary coils for a transformer. Well, let's look at how a transformer works. Well, Alright, so we've got an oscillating current in this. So currents get big and back the other way, back and forth all the time. So you've got an oscillating electric field. That's creating a what? A changing magnetic field. Now because this is iron, most of the magnetic field will tend to stay in the iron. And iron kind of gives it like a pathway to go through. It's easier to travel through the iron than through the outside. So most of that magnetic field will travel, and now you've got a changing magnetic field running through a coil of wire. Now what did we say last time? A changing magnetic field will actually induce an electric field in the wire. So now we get an electric field induced in the wire. Now if there's an electric field induced, you're going to measure the potential difference of the electric field with the voltmeter. So this won't just separate charge. That's what electric fields do. They produce charges. So you're going to start pushing charges one way and separating the positives from the negatives on the charge. So what you basically do is you've got an oscillating source on one side, creating in these coils that it doesn't touch. It doesn't touch. Just sitting there. It basically creates a voltage over here. Now, some of those inductive chargers some of you may have for your phones, it works the exact same way, except it's just not a coil of wire. You have the coil up here, one's here, and one's there in your car. Now, those have heating issues. If those use those, they tend to get a lot warm sometimes. Then you have to have a system of coils in your phone or something to charge it up that way. I mean, it works. It's not the most efficient way. This going iron core helps make these transformers much more efficient. But it's the same concept of those inductive chargers, except you've got a coil of wire. Now, in this case, though, this is important. The ratio of the coils, now let's think about it, makes a difference. What if you have a whole lot of coils here? I mean, coils like crazy, hundreds of coils over here. You're going to pick up a lot. And so you have just a few coils here. What they found was that the voltage you get induced here is a function of the ratio of the coils. If you've got the same amount of coils here that you have there, you've got 5 volts going in, 5 volts coming out. Now, of course, it's an oscillating AC input to it. Say you've got double the amount of coils on your secondary versus the primary. Well, if you've got 5 volts coming in, you can have 10 volts AC coming out. Say you like these fluorescent light bulbs we have. If you've got fluorescent lights in your house, they talk about high voltage. Those things may be 1,500, 2,000 volts, 1,000 volts. I'd have to look it up. But it's high voltage. It's in a couple thousands of volts. Well, we got 110 going into it. So they've got a transformer. It's called the ballast in these, if you put up a fluorescent light system, there's a ballast in there. What that does, that basically converts 110 to 1,500 to 2,000 volts. So how's it going to go from 110 volts to 2,000 volts? Well, it's going to have almost 20 times the number, 20 times more coils on the secondary side of the transformer in that ballast versus the primary. And why has that got stuff all around it? They don't want you to touch it and everything. Because that's a lot of voltage, and that voltage will get you, shock the heart. It's not good. Especially the amount of current load that comes through this. Now, the current, of course, is a function of the resistor over there that you have in it, the resistance in it. But that's the way those ballasted transformers work. Now, let me give you the equation for this. It's pretty simple. It's just a ratio equation. And that ratio is that the voltage in the secondary is equal to N2 over N1 times the voltage going into the primary. And that's just, that ratio there will determine if you step up the voltage, if you increase it, it's called a step-up transformer, or if you decrease the voltage, that's a step-down transformer. If you look at your house, coming into your house, my house is out by itself, so I've got my own transformer just for my house. Sometimes there'll be transformers going to 2 or 3 houses or something. But it sends voltage out on those high power lines that you get, the real tall ones. You're not supposed to touch them. There's thousands of volts running through those and a whole lot of current. If you touch those, you die most of the time. Now, why do they have going into each house? They have one transformer going into each house. Now, if you ever see a transformer blow up, when they just short each other out, that's cool. But that's another story. Lightning strikes them or something. But what you've got in that cylinder that comes into your house is something like this. On the input side, there's so many coils. Now, that's a step-down transformer because it wants to take 110 or 220 coming into your house. It's going to step it down. So it's going to have fewer coils on the secondary side than the primary side for that voltage coming into your house. That's a step-down transformer. Okay? course, one of the biggest issues, I don't know if you think about transformers, the power company has issues with is squirrels or animals getting into these, and their tails will sometimes go across these, or they'll go across wires that shouldn't, say, like right here, or touch something else. And so the squirrel becomes a wire, and then you get, shish kebab or barbecue. Definitely fried, very flash fried squirrels or whatever. Yes. The big power stations where you see them, substations, they basically are taking higher voltage and sending it out at lower voltage. So basically they've got giant cylinders, big cylinders in rooms, taller than I am at times, some of them. They're just transformers with 2 sets of coils of wire. Now they've got electronics to keep it smooth, and there's other things. But that's the basic idea of transformers. Basic idea of the transformer. Okay. All right. And by the way, the wall warts, you call them, the things you plug in the wall and they get 5 volts out. Well, remember, you got to have, this has to produce current going in like this. If this is time, and that's voltage, it produces oscillating signals like this. That's AC. Now, coming out, of course, you have to have AC as well. Of course, that's time, and that's voltage. And it'll be a different voltage based on the ratio of these. Now, a lot of you guys use these for like your USB. How do you get USB to go from, and that's DC, that's direct current, like your phones and stuff. Actually, what they do is, your wall wart, your thing you plug in, you plug the USB cord in, it's got a little transformer in there. And, oh, by the way, why do they like the 2 amp and the 3 amp transformers, or the little devices that go output 2 amps and 3 amps? Why are they more than one? Why are they more expensive than 1 amp? Well, they got more coils of wire. They have to be able to deal with more current coming out of it, I should say, and coming into it because they pull more current coming in. Now, how do they put out DC? They actually don't. What they do is they take this negative side of it from that sine wave right there in the AC. They take that negative side and they just flip it. Have a little inverter in there, and they flip it. And they might have, if it's a good one, they might have a little electronics that will make it not go all the way down to 0. And it'll go like this. But if you look at what's coming out of like a transformer out of your electrical socket, and it goes and it say it outputs 5 volts DC. If you read them, they'll say like 120 volts AC, 5 volts DC. They just have a transformer, and if they make DC, it's an inverter. And if you look at this with an oscilloscope, that's what you would see. That's kind of cool. Now, does a batteries produce real DC? Batteries are flat. So if you really want a nice smooth signal, use batteries. This voltage variation can, I think I told you guys, I fried laser diodes using stuff because I had too much of this in the past. Alright, so that's transformer. Let's look at metal detectors real quick. Metal detectors. Now, metal detectors basically are similar. You have, let me get the names right for this. Basically, you have a transmitter coil, and basically you have a receiver or pickup coil. Now, this is what, like a transformer. This has so many coils of wire in it. This has so many coils, and by the way, the more coils you get here, the more sensitive this can be. Of course, that's why the big expensive, the real good metal detectors, besides the electronics, has more coils of wire in it. They cost more. All right. So, electricity is running threaded right round, baby, right round here. As that goes round and round, that's going to produce a magnetic field, a changing magnetic field. Because this is, I'll make this, it's AC current going into it. So if this has a changing magnetic field going into here, you've got a changing magnetic field, and that's going to make some voltage coming out, because that's going to induce a voltage. Changing magnetic field will induce an electric field, which will cause a voltage. Now, that's nice and simple. Now, you notice you don't have two separate coils. Normally, what you do have, they're kind of together if you look at how a metal detector is. But this is just for demonstration purposes. What happens is, let's put some metal piece in here. Some jagged metal piece. Well, that's metal. So it's going to produce eddy currents. Remember, those eddy currents are produced in such a way to resist that from happening. So we'll just say the eddy currents are like in this direction. Now those eddy currents are produced. What do those eddy currents produce? Well, they produce their own magnetic field themselves. So you've got, and I'll say B from the eddy current caused by that metal being there. Now this B from this eddy current is also picked up by the B in this receiver coil. So what I will say is that the B total is equal to the B field, and this can have direction as well. So I'm going to use vectors here. The B field from the transmitter, and that one would be a constant value. But there would also be, and this can be positive or negative, a B field from the eddy current produced by the metal system in there. Produced by the metal in there. All right. Now you notice with how do you make these more sensitive? You swing them. People swing them. By swinging them, you're also creating a changing magnetic field here. And by swinging them as well, they can get over time. They can get an idea of what this change looks like, and that's why you can see these shapes. Of course, a bigger piece of metal, bigger right here, so that gives you a bigger, stronger signal. But that's the way they work. And of course, a coin's going to have a different signal than a jagged piece of metal. And what they've done over time, they've kind of effectively get to know, they've effectively trained, they've looked at, I won't say AI, but basically have figured out, all right, coin looks like this, a silver coin, people look at it, so they kind of know. So they've got, rather than just having a little meter there, they use electronics now, little controllers there, right? If it looks like this, it's probably that, looks like that, it's probably, it's a silver, that's a pop top. That's the biggest thing with metal detectors, how it's different between a pop top and a coin, because they look real similar. So if you can discriminate between those, a whole lot of pop tops you dig and you get absolutely no value out of it. Recycling guys aren't going to look at dig, of course. But coins, that's a different story. All right, so that's why that change in the eddy current for pop tops and coins is real similar. That's why the real more expensive metal detectors can discriminate that a lot better than the cheap ones. Okay? Metal detectors. Kind of cool. That's it for today. Next one will be chapter 31.